The diameter of the Boötes void measures roughly 0.3% of the diameter of the observable universe, a fraction so small that on paper it resembles a rounding error rather than a structure. Converted into volume rather than length, that same fraction expands into a region wide enough to have once been expected to hold several thousand galaxies, each containing hundreds of billions of stars. The discrepancy between how small the number sounds and how large the resulting structure actually is forms the starting condition for everything that follows. Because at cosmological scale, a negligible percentage and a negligible object are not the same thing. And confusing the two is the first error any analysis of this system must avoid. Understanding why a region this size can exist at all requires beginning not with the void itself, but with the architecture that surrounds it, since no underdense region forms in isolation from the structure around it. The observable universe, when mapped across hundreds of millions of light-years rather than the scale of individual galaxies, does not resolve into a uniform haze of matter spread evenly through space. It resolves, instead, into a connected lattice, now generally referred to as the cosmic web, composed of 4 recurring structural elements that repeat at every scale large enough to map. Long, thread-like concentrations of galaxies, called filaments, stretch across distances that can exceed 100 million light-years, carrying matter along their length, the way a riverbed channels water across a landscape. Where multiple filaments converge, the result is a cluster, a dense gravitational knot containing anywhere from hundreds to thousands of galaxies packed into a comparatively small volume, bound tightly enough that the expansion of space itself struggles to pull them apart. Between filaments, broader and flatter structures called walls extend across the gaps, composed of galaxies distributed more thinly than in a filament, but still well above the cosmic average. And occupying the remaining space, filling the gaps between filaments, clusters, and walls, are the voids, regions where galaxy density falls dramatically below what the rest of the universe would predict. This 4-part structure is not decorative, it is functional, in the sense that each component exists only because the others exist. A filament cannot form without a corresponding region losing the matter that the filament gained. A cluster cannot grow without filaments feeding matter inward from multiple directions simultaneously. And a void cannot deepen without its surrounding filaments and walls pulling material outward and away from it across vast stretches of time. The system functions as a single mechanism of redistribution operating at the largest scale that gravity is capable of acting upon, and the Boötes void is best understood not as an anomaly sitting apart from this mechanism, but as one output of it, occupying the same structural category as every other void in the observable universe, distinguished only by its scale. The conditions that allowed this redistribution to begin trace back to a period of cosmic history far removed from anything resembling a galaxy, filament, or void. Roughly 380,000 years after the initial expansion of the universe, the cosmos cooled enough for free electrons and protons to combine into neutral hydrogen atoms for the first time, a transition that allowed light to travel freely through space rather than being constantly scattered by charged particles. The light released at that moment still survives today, stretched by billions of years of cosmic expansion into faint microwave radiation that fills the entire sky in every direction, now studied under the name cosmic microwave background radiation. When this radiation is mapped across the sky, in fine detail, it does not appear perfectly uniform. It contains extremely small temperature variations, on the order of a few parts in 100,000, scattered unevenly across the observable sky, in a pattern that at first glance looks like noise, but on closer analysis reveals a structured signature. These temperature variations are not incidental texture. They are direct evidence of density variation in the early universe, recorded at the precise moment light was first permitted to travel freely. Slightly warmer regions of the cosmic microwave background correspond to regions where matter was marginally more concentrated than average at that early stage, while slightly cooler regions correspond to areas where matter was marginally less concentrated. The word marginally carries real weight here, since the differences being described amount to fractions of a single percent, differences so small that in almost any other physical system they would be considered negligible and discarded as measurement noise. The early universe did not contain dramatic clumps of matter sitting next to dramatic gaps. It contained an almost featureless distribution disturbed by whispers of asymmetry, too faint to register as anything significant on their own. The origin of those whispers lies in the behavior of matter and energy at scales far smaller than anything directly observable, governed by the same uncertainty that defines quantum-scale physics generally. In the earliest fractions of a second after the initial expansion began, the universe was compressed into a volume small enough that quantum fluctuations, ordinarily confined to subatomic scales, became the dominant source of variation across the entire system. As the universe expanded at extraordinary speed during the period now described as cosmic inflation, those minuscule fluctuations were stretched along with the fabric of space itself, scaling upward from quantum dimensions to cosmic dimensions without losing the pattern of variation they originally contained. What began as the faintest possible asymmetry, operating at a scale smaller than anything a particle accelerator could probe even today, became the template for every structure that would eventually form across billions of years of subsequent history. This is the principle that governs the entire system and explains why a structure as extreme as the Boötes void was permitted to form at all. Gravity does not create asymmetry. It amplifies whatever asymmetry already exists, and it does so without limit as long as time continues to pass. A region with even a fractionally higher density than its surroundings exerts a fractionally stronger gravitational pull, drawing in additional matter from its immediate surroundings, which increases its density further, which increases its gravitational pull further still. The process compounds continuously rather than reaching equilibrium, in the same way that a small numerical advantage compounded repeatedly over a long enough period produces an outcome far larger than the original advantage would suggest. A region with fractionally lower density experiences the inverse of this same process, losing matter to its denser neighbors at a rate that accelerates rather than levels off, becoming progressively emptier as billions of years pass rather than stabilizing at some moderate deficit. A region of marginally lower density does not remain marginal indefinitely, left to operate across billions of years. The compounding process described in the previous section eventually produces something far more specific than ordinary underdensity, and the mechanism responsible for that escalation begins at the boundary, not the center, of a forming void. The boundary of an underdense region is where the gravitational asymmetry first becomes consequential. Matter sitting at the edge of a low-density zone experiences a measurable pull toward whatever denser structure happens to lie just beyond that edge, whether a forming filament, a wall, or the outer reach of a cluster still gathering mass from its surroundings. That pull does not need to be strong to be effective, since it operates continuously across timescales long enough to make even a weak gravitational gradient decisive. Galaxies, and the gas clouds that would otherwise have condensed into galaxies, drift outward from the boundary toward the denser structure, a process generally referred to as gravitational drainage. As that material departs, the boundary itself does not stay fixed in place. It shifts inward, into territory that had previously belonged to the denser surrounding structure, meaning the underdense region does not merely lose matter, it physically expands, claiming additional volume as its edges deplete. This drainage process explains how an ordinary void deepens over time, but it does not, on its own, account for a structure as extreme as the one under analysis here. Ordinary voids produced by straightforward drainage tend to settle at diameters in the range of several tens of millions of light-years, a scale at which the boundary effect eventually reaches a kind of equilibrium, since a region can only expand so far before the gravitational gradient pulling matter outward weakens past the point of being effective. The structure under analysis, by contrast, spans roughly 330 million light-years across, centered at a distance of approximately 700 million light-years from Earth, dimensions that place it well beyond what single-region drainage operating in isolation would be expected to produce within the age of the universe. Something beyond the basic boundary mechanism was required, and the leading explanation for that additional step involves not one underdense region forming and expanding on its own, but several. The model generally favored to account for structures of this magnitude is known as void merging, and it operates on a premise distinct from simple drainage. Rather than beginning as a single seed of underdensity that grows outward uniformly in every direction, The process begins with multiple smaller underdense regions forming independently, separated from one another by thin walls of galaxies, walls thinner and less massive than the dominant filaments and clusters that anchor the wider cosmic web. Each of these smaller voids undergoes the same drainage process described above, expanding gradually as matter departs from its edges. Because the separating walls between adjacent voids are comparatively thin and comparatively low in density to begin with, they are uniquely vulnerable to the same gravitational drainage acting on them from both sides simultaneously. Matter departs the wall in two directions at once, toward each of the underdense regions it separates, accelerating the wall's depletion well beyond the rate at which a filament or cluster boundary would deplete under equivalent conditions. As a separating wall thins past a critical threshold, it ceases to function as a barrier between the two regions it once divided. The underdense zones on either side, no longer kept apart by a structure dense enough to resist gravitational drainage, effectively become a single contiguous volume. What had been two distinct voids, each with its own history of formation and its own rate of expansion, merges into one composite structure substantially larger than either original region. Repeated across several such merger events, occurring at different points in cosmic history and involving void seeds of varying initial size, this process is capable of producing a structure whose final diameter far exceeds what any single seed of underdensity could have achieved through drainage alone, operating within the same span of available time. This sequence carries a specific consequence for what remains inside the merged structure once the process concludes, and that consequence is the detail that makes the model verifiable rather than purely theoretical. Not all of the matter occupying a separating wall departs cleanly before the wall collapses. Galaxies positioned deep within the wall's interior, farther from either underdense region than galaxies positioned near the wall's outer face, experience a comparatively weaker gravitational gradient pulling them toward any single direction. Pulled with roughly equal weakness from both sides at once, some of these interior wall galaxies fail to drain in either direction before the wall thins past the point of structural coherence. When the merger completes, these stranded galaxies do not vanish or relocate. They remain exactly where the old wall used to stand, now surrounded on all sides by the underdense interior of the newly combined void, marking the former boundary the way a discontinuity in stratified rock can mark a fault line long after the geological event that produced it has ended. The arrangement of galaxies confirmed within the structure under analysis bears the signature this model predicts. Rather than scattering randomly through the available volume, as a single void formed and expanded from one uniform seed would be expected to produce, the confirmed galaxies trace a rough linear path running through the interior, consistent with the position a stranded wall would occupy following the merger of two or more smaller predecessor voids. This is not the only line of evidence supporting the merger model, but it is the most direct, since a purely random distribution and a merger-derived distribution would be expected to leave visibly different fingerprints, and the fingerprint observed favors the latter. The merger model also resolves the timing concern raised by the scale of the structure under analysis. A single void seed expanding through drainage alone, operating across the full 13.8 billion years since the early universe, sits uncomfortably close to the upper limit of what that mechanism can plausibly achieve at this diameter, a tension that drew considerable scrutiny when the structure was first measured in detail. Multiple smaller seeds, each beginning the drainage process independently and at varying points across cosmic history before eventually merging, removes that tension almost entirely. The final structure need not have been built by one continuous process operating at maximum efficiency for the full span of cosmic time. It could instead represent the cumulative result of several more modest processes, each individually unremarkable, compounding through merger into something that appears extreme only when viewed as a single object rather than as the sum of its formation history. A galaxy stranded along a former wall boundary does not simply persist unchanged once the surrounding structure that once fed it has dispersed. Its subsequent development depends entirely on resources that, inside this environment, are no longer reliably available, and tracing what happens to those resources reveals how the interior of the structure actually functions once formation is complete. Galaxy growth, under ordinary conditions within a filament or near a cluster, depends on a continuous supply of cold gas flowing inward along the same channels that carry galaxies themselves toward denser regions. This gas serves as raw material for ongoing star formation, replenishing what a galaxy consumes and allowing new generations of stars to ignite as older ones exhaust their fuel and fade. A galaxy embedded within an underdense interior, far removed from any filament capable of supplying this inward flow, does not have access to the same replenishment. Whatever gas it retained at the time it became isolated is largely what it will continue to draw upon going forward, since the surrounding volume offers no equivalent mechanism for restocking that supply. The result is a gradual decline in star formation rate relative to galaxies of comparable mass and age still embedded within active filaments, a decline that compounds over time as the available gas reservoir is steadily consumed without meaningful renewal. This altered growth trajectory leaves a measurable signature in the galaxies confirmed within the structure under analysis. Observational surveys examining their stellar populations find them skewing older on average than galaxies of similar total mass located in denser environments, with a noticeably reduced proportion of young, hot, short-lived stars relative to what filament-dwelling counterparts typically display. The chemical composition of these galaxies tells a related story. Heavier elements, everything beyond hydrogen and helium, are synthesized inside stars and released into surrounding gas when those stars die, meaning each successive generation of star formation enriches a galaxy's gas supply with progressively more complex chemistry. A galaxy that has undergone fewer cycles of star birth and death, constrained by limited gas availability, shows correspondingly slower chemical enrichment, its overall composition lagging behind what an equivalent galaxy in a richer environment would have achieved across the same span of time. This pattern of isolation extends beyond visible matter into a component that cannot be directly observed at all. Surrounding every confirmed galaxy in the universe, including each of the galaxies identified within this structure, is a halo composed of matter that emits no light and interacts with ordinary matter almost exclusively through gravity, generally referred to as dark matter. Current estimates place the total quantity of dark matter in the universe at roughly 5 times the quantity of ordinary matter, meaning it forms the dominant gravitational scaffolding around which visible structures such as galaxies, filaments, and clusters assemble themselves. Its presence is inferred not through direct detection, but through its gravitational effect on the motion of visible matter and on the path of light passing near concentrations of it, an effect that has been measured consistently across decades of observation. Within an underdense interior, dark matter follows the same depletion pattern as ordinary matter, having drained outward during the formation process described previously, governed by the identical gravitational gradients that pulled visible gas and galaxies toward the surrounding filaments. The galaxies that remained stranded along the old wall boundary retained their individual dark matter halos, since a galaxy's immediate halo is gravitationally bound closely enough to travel with it rather than being stripped away during the broader drainage process. But these halos formed and grew within an environment that supplied far less surrounding material than a filament environment would have provided, leaving them measurably smaller than the halos surrounding galaxies of comparable mass located in denser regions of the cosmic web. The boundary separating the underdense interior from the surrounding cosmic web is not a sharp threshold, but a gradual transition, and dark matter behaves distinctly within that transition zone compared to how it behaves either deep in the interior or far out within the surrounding filaments. As matter drained outward from the interior across billions of years, a portion of it did not travel the full distance to the nearest dense filament or cluster, instead settling temporarily at the boundary itself before continuing its outward migration at a slower rate. This produces a subtle increase in both galaxy density and dark matter density concentrated specifically at the edge of the underdense region, a feature generally described as a void shell. The shell is not a wall in the structural sense established earlier, since it lacks the coherence and thickness that once characterized the boundaries between the smaller progenitor voids prior to merger. It is instead a gradual thickening, a zone where the near-total absence of matter characterizing the deep interior begins giving way, incrementally, to the richer density of the surrounding web. This gradual thickening carries a specific observational consequence relevant to galaxies positioned within it, rather than deep within the interior. A galaxy located near the boundary, rather than at the structure's geometric center, occupies an intermediate position between two distinct resource environments. It receives some benefit from gas flows beginning to organize along the nearest filament, modest compared to what a galaxy fully embedded within that filament would receive, but measurably greater than what a galaxy isolated, deep within the interior can access. Star formation rates among boundary-positioned galaxies consequently fall between the two extremes already described, neither matching the suppressed activity typical of the deep interior, nor approaching the sustained activity typical of filament-embedded galaxies elsewhere in the web. This creates a continuous gradient running from the structure's center outward to its edge, with galaxy age, chemical composition, and star formation rate all shifting incrementally along that gradient rather than dividing sharply between an empty interior and a populated exterior. The presence of this gradient, rather than a hard boundary, becomes one of the more useful features of the structure for testing whether its formation history matches the predictions established in the previous section. A structure built through simple, single-seed drainage would be expected to produce a particular gradient profile shaped by one continuous expansion process operating from a single point outward. A structure built through the merger of several smaller progenitors, each with its own drainage history prior to combining, would be expected to produce a gradient with more internal variation, reflecting the layered histories of its component parts rather than one uniform process. Current measurements of the galaxies and inferred dark matter distribution within this structure are detailed enough to suggest a gradient consistent with the merger interpretation, though not yet precise enough to rule out alternative explanations entirely, a limitation rooted in the resolution achievable by current survey instruments at the distances involved. The gap between suggestive data and confirmed certainty is not unique to the gradient measurements described above. It extends to a more fundamental question that has accompanied this structure since the scale of its underdensity was first calculated with confidence, namely, whether a structure this size and this empty falls within the range of outcomes the standard model of cosmic structure formation can comfortably produce, or whether it sits close enough to that model's outer limit to warrant treating it as a genuine point of tension. The standard framework against which this question is measured is generally referred to as lambda-cold dark matter, abbreviated as the lambda-CDM model, a description of cosmic evolution that combines the gravitational amplification mechanism established earlier in this analysis with two additional components: a form of dark matter that interacts gravitationally but otherwise weakly with ordinary matter, and a uniform energy density, referred to as dark energy, responsible for the accelerating expansion of space itself. This combined framework has been tested against an extensive range of observations, including the detailed structure of the cosmic microwave background, the large-scale clustering of galaxies across multiple independent surveys, and the relative abundance of light elements produced during the earliest minutes of cosmic history. And it has matched those observations with a level of consistency that has made it the dominant working model in the field for several decades. Testing whether this model can comfortably account for a structure of the scale under analysis here requires a specific kind of test, distinct from comparing the model to an average outcome. Researchers generate large numbers of simulated universes, each built by running the same underlying physics forward from initial conditions consistent with the measured properties of the early universe, then examine how often those simulated universes produce an underdense region matching the dimensions confirmed for the structure under analysis. This approach treats the question not as whether the model permits a structure of this size, since virtually any outcome is permitted somewhere within a sufficiently large set of simulated universes, but as how frequently that outcome appears, which determines whether its existence here represents an unremarkable result or a statistically uncomfortable one. The result of this kind of testing places the structure under analysis near the upper boundary of what repeated simulation runs typically produce, a position generally described using the language of rare statistical events rather than impossible ones. A result of this kind does not indicate that the simulated framework has failed to reproduce the observed universe, since rare outcomes are an expected feature of any model that incorporates genuine randomness in its initial conditions. The same randomness traced earlier in this analysis to quantum scale fluctuations stretched across the inflationary period. It indicates instead that finding a structure of this magnitude requires landing somewhat further into the tail of the distribution of possible outcomes than finding a structure of more typical, underdense dimensions would require, a distinction that matters statistically without necessarily mattering physically. The discomfort this result generates among researchers studying the structure is not primarily about this one void considered in isolation. It is about the pattern formed when this result is placed alongside a small number of other large-scale structures identified through independent surveys, each of which occupies a comparably rare position within the same kind of statistical distribution. A flattened concentration of galaxies extending across billions of light-years, identified through systematic mapping of galaxy positions across a wide region of sky, occupies one such position. A region of unusually low temperature identified within the cosmic microwave background, persisting after accounting for instrumental effects and known sources of measurement noise, occupies another. Considered individually, each of these results remains within the range the standard model permits, however far into that range it sits. Considered collectively, the recurrence of multiple independent structures, each requiring a similarly rare outcome, begins to raise a more general methodological question about whether the underlying model has been correctly calibrated, rather than a specific claim that any one structure disproves it. This methodological question carries a recognized term within the broader scientific literature, generally described as fine-tuning, referring to situations where a model can technically accommodate an observed result only by repeatedly relying on outcomes drawn from the rare end of its predicted distribution. A single instance of fine-tuning is rarely treated as decisive evidence against a model, since any sufficiently complex system will occasionally produce unlikely results purely by chance. Repeated instances, particularly when they involve structures unrelated to one another in cause and location, shift the conversation from isolated curiosity toward a pattern worth examining systematically, though shifting the conversation is distinct from overturning the model itself. The position held by the majority of researchers actively working on this question treats the structure under analysis and the handful of comparably extreme structures associated with it in this broader conversation as consistent with the standard model once the full statistical range of permitted outcomes is properly accounted for, rather than as evidence requiring a modification to the model's underlying physics. This position rests on the observation that rare events, by definition, must occur somewhere within a universe large enough to contain billions of underdense regions of varying size, and finding one or several examples sitting near the statistical edge of what is permitted is itself an expected consequence of surveying a large enough volume of space rather than a sign that something has gone wrong with the surveying or the underlying theory. Classification near the edge of a permitted statistical range is not a permanent designation. It is a snapshot drawn from the precision of the instruments currently available, and the instruments responsible for that snapshot are continuing to improve at a pace that makes the current classification provisional rather than final. The consensus picture presently held by the majority of researchers working in this field treats the structure under analysis as a large, genuinely rare, but ultimately explicable product of the same formation process responsible for every other underdense region in the observable universe, requiring no departure from the standard framework to account for its existence. This consensus is built not from a single decisive measurement, but from the cumulative weight of multiple independent lines of evidence converging on the same conclusion, the gravitational amplification mechanism established early in this analysis, the void merger sequence capable of producing a composite structure at this scale, the residual galaxy distribution consistent with that merger history, and the statistical modeling confirming that outcomes of this magnitude, while uncommon, remain within the range the standard framework permits. None of these lines of evidence, considered alone, would constitute a complete account. Combined, they form the most coherent explanation currently available, and the field's working position rests on that combination rather than on any one component in isolation. This consensus does not exist in isolation from the broader catalog of comparably extreme structures referenced in the discussion of statistical tension, and situating the structure under analysis within that catalog clarifies rather than complicates its position. A flattened concentration of galaxies extending across roughly 10 billion light-years, identified through systematic clustering of high-energy cosmic events across a wide survey region, represents one of the largest structures presently cataloged, dwarfing the underdense region examined throughout this analysis by a substantial margin in linear extent. A separate underdense region inferred to surround the broader neighborhood containing Earth's own galaxy, extending across roughly 2 billion light-years and exhibiting a density deficit of several tens of a percent relative to the cosmic average, represents a different category of structure entirely, distinguished less by its emptiness and more by the methodological difficulty of measuring a region from a vantage point situated near its center rather than observing it from the outside. The unusually cool region identified within the cosmic microwave background, persisting after instrumental effects have been accounted for, represents a third category, tracing not the present-day distribution of galaxies, but a much earlier signature imprinted before galaxies existed at all. Each of these structures occupies a distinct place within the same broader conversation about rare outcomes and statistical tension, yet none of them, including the structure under primary analysis here, has produced a result definitive enough to require revising the underlying framework. What their continued cataloging has produced instead is a steadily improving picture of how frequently structures of this general category occur across the observable universe, a picture that grows more precise with each additional survey rather than remaining fixed at the level of detail available when the structure under analysis was first measured in detail decades ago. That improving precision is the product of a specific generation of observational tools designed to map galaxy positions and distances across far larger volumes of sky than earlier surveys were capable of covering, while simultaneously achieving finer resolution on the distances and properties of individual galaxies within those volumes. Ground-based spectroscopic instruments, dedicated to measuring the redshift of tens of millions of galaxies across substantial fractions of the observable sky, are producing three-dimensional maps of cosmic structure with a density of data points that earlier redshift surveys, limited to narrow fields and comparatively small galaxy counts, could not approach. Wide-field imaging surveys, capable of photographing large areas of sky in single exposures and repeating those observations across extended observing campaigns, are building statistical catalogs of underdense regions across far greater volumes than any single survey previously achieved, allowing researchers to compare the frequency and properties of structures at this scale against simulated predictions with considerably tighter statistical confidence. Space-based instruments, freed from the atmospheric distortion that limits resolution for ground-based observation, are contributing precise measurements of how light bends as it passes near concentrations of matter, a technique that maps the distribution of dark matter directly rather than inferring it solely from the positions of visible galaxies. Applied specifically to the structure under analysis, this improving observational capacity is expected to refine several of the open questions raised across the preceding sections, rather than leaving them permanently unresolved. The precise boundary between the structure's deep interior and its surrounding shell, currently understood only as a gradual transition without sharply defined edges, stands to be mapped with considerably greater resolution as wide-field surveys extend their coverage to include the full volume the structure occupies. The population of fainter, lower luminosity galaxies that current instruments may have failed to detect within the interior, a population whose existence would not eliminate the structure's overall deficit but could meaningfully adjust its precise magnitude, stands to be more completely cataloged as deeper imaging campaigns reach fainter detection thresholds at the relevant distance. And the internal gradient distinguishing a single seed formation history from a multiple merger formation history, currently suggestive but not yet conclusive, stands to be tested with considerably greater statistical confidence as the total number of confirmed galaxies and their measured properties within the structure continues to grow. None of these refinements are expected, based on the trajectory of evidence accumulated so far, to overturn the structure's basic classification as a large but explicable underdense region produced through standard gravitational processes operating across cosmic history. They are expected instead to convert what currently stands as the most probable explanation into a far more precisely confirmed one, narrowing the remaining uncertainty without requiring a fundamentally different account of how the structure came to exist. This is the ordinary trajectory of an unresolved question within an active scientific field, not a sudden resolution arriving from a single decisive observation, but a gradual tightening of confidence as successive generations of instruments bring incrementally sharper data to bear on a question that has remained open in its essential form since the structure was first measured with enough precision to recognize how unusual it actually was. The structure's current position within the broader system it belongs to, then, is neither a fully resolved case nor a genuinely open anomaly, but something more specific, a known and largely understood output of a well-established formation process, whose remaining uncertainty is shrinking steadily rather than persisting indefinitely, and whose ultimate significance may rest less on whether it confirms the standard model than on what its precise internal structure, once fully mapped, reveals about the conditions present in the universe during the earliest moments of its existence,